I thought we would just take a quick, because the main part of that is dealing with the perspective projection. I thought we'd just have a quick review of it and do a bit of a demonstration of it, or to try and persuade you that the mathematics we've described here does indeed do what it claims to do. And so we'll actually see, we'll generate on the computer a simple scene with some basic shapes in it, and produce a perspective projection of that. Okay. So just to remind you, the setup for perspective projection was this, where now we're dealing with an aligned environment. So an aligned environment is where the viewpoints, remember, to obtain any kind of view of the environment, you have to specify two things: a position for the viewer, the virtual camera, position for the viewer, and a direction of view, where the viewer is pointing. Where am I looking? So you can think of that as specifying 2 points, or the viewpoint and the viewing vector equivalently. They're equivalent things. Now, for the purposes of this discussion here, we'll assume that the environment has been aligned, so that the environment has been translated and rotated, so that now the viewpoint is sitting at the origin, and the direction of view is along the positive z-axis. Okay. So that is the setup depicted here. We've got the viewpoint at the origin, and the viewpoint is looking along the z-axis. So this house object type thing is centered on the z-axis, and this thing we're going to talk about now, the projection plane, is centered on the z-axis as well. And so the perspective projection is produced by modeling the basic idea of what goes on with the eye. Okay, so light rays are reflected off the objects in the world, and you only see those light rays that hit your eye. And for the purposes of this, we'll assume that your eye is a point object. Okay, so the only light rays that are perceived are those that hit the origin exactly. Now, in your actual eye, the image is projected onto the curved back of your eye, onto your retina. And that image is sensed by the cells in your retina and sent to your mind or your brain. In this setup, we bring the projection plane, not the back of some eyeball here, but we push it out in front of the eye, and imagine it as a flat plane, parallel to the XY axis and situated at some point along the Z axis. So we insist it's parallel. So what we need to know to determine its exact location is just its distance f from the origin. Okay, the distance of the plane from the origin as you move along the z-axis, the perpendicular distance from the origin to this plane. And you can kind of think of that, imagine that as if holding up a sheet of glass in front of your eye. And to produce a perspective projection, to produce a 2D image of what you actually see, you could imagine fixing that plate of glass on a stand here in front of me. I could pick a pen and I could close one eye, so I could just pretend I'm just using one eye, and then I could actually trace out everything. I could draw out everything I see on the glass, on the sheet of glass with a black pen. You know, I could draw, and if there was a road disappearing into the distance, I'd draw the lines that I can see. So I'd be drawing these lines for the edge of the road. They kind of move up the sheet of glass and are moving up towards each other and are seeming to meet at some point in the far distance. Well, metaphorically, that's what we're going to do here. We're going to take each projector line, which is coming off the scene, off a vertex in the scene, and towards off a vertex or a point along a line in the scene, and towards the eye, and we're going to record where they intersect the projection plane. Okay, so that's like me drawing on the sheet of glass what I can see beyond the glass. So taking these points and sending them onto the point where these projector lines intersect the screen, that's going to trace out this image on the projection plane, sheet of glass, so to speak, of what the viewer sees in the world. Okay, and so it will look like a fairly realistic depiction. Realistic in the sense that it picks up the depth information, you know, the lines that are actually parallel, they do tend to come together in their vanishing points and so on. And we can get a very good impression of the relative positions of the objects in the scene. Things in the distance will look smaller. Things up close to the viewer will appear larger in the perspective projection, okay? Which they don't in the orthogonal projection. Orthogonal projection just sends everything perpendicularly towards the projection plane, and so sizes aren't, the size of the image on the projection plane isn't changed. It's exactly the size of the object in the real world. Okay, so this is all about lines from points in the world to the origin and where they intersect the plane. So it's readily done using the language of vectors and components and so on. Okay. Now we described the basic method was, okay, we kind of described it in terms of matrices, but you can't actually do it. It's not an example of a linear transformation, so it can't, well, yeah, it's kind of easiest to think of it as a transformation on the level of the components of the vector, okay? So we consider if you've got a point with coordinates x, y, z in the world, if you've got a point with coordinates x, y, z in the world, then these will be the coordinates of the corresponding point on the projection plane, okay? So this will be its perspective projection of the point with coordinates x, y, z onto the projection plane. So you see they all have z coordinate f. That makes sense because these are all points that are supposed to be living on the projection plane. And the projection plane is located at z equals f. Looking at the diagram up here, the f is the distance here, so the projection plane is situated at z equals f. Every point on the plane has z coordinate f. Remember, z is going off that way towards the house from the origin. And the x and y coordinates are transformed like this. So it's x times f over z and y times f over z. So you can see here that how it's going to make points in the distance small, because points in the distance in the virtual world are points with large z value, points that are far away from the viewpoint, for instance, in the direction that the viewer is looking. So points with large z value, large positive z value, well, because z is in the denominator there, that's going to shrink those down and make the, you know, as the point goes further and further into the distance, these values are going to tend to be small. And if points are far away, from each other, so two points that are far away in the distance from you, but say the points are a mile apart, so their x coordinates, say, will differ by 1 mile. Well, the further away in the distance they are, the less significant that will be. If the difference between their x coordinates is a mile, but the points themselves are 10 miles away, in fact, they'll in the perspective projection, they'll only appear to be 1/10 of a unit apart, 1/10 of a mile, or whatever, okay? So it's the presence of this z in the denominator that kind of shows you the shrinking effect of things in the distance. Okay. Okay, now last time we did a bit of work with to answer exercise 7.2. We drew a couple of views of the situation. And it's hard to track exactly the values of what's going on here, but we looked at two views of this. We looked at a view from above, so a view from up high on the x-axis looking straight down. So we drew the y and z axis, and we could track that transformation, how it affects the y coordinate of the point. And then we looked at a side view, looking just at the x and z plane from a point on the positive y-axis. And by tracking these lines and that, we were able to look, I've actually got my x and y the wrong way around. Did I point that out last week? I should have. I should change that y and x to go the other way around. Anyway, we produced the side view of this, looking at this vertical plane, which should be the yz plane, and saw that that transformation was the correct one as well. Okay. So what I'd like to do now is I've prepared this sheet here. So this is in the computer system Sage, the online version of Sage, and I'll I've got some commands here that are going to simulate this setup. And we'll actually be able to see, it's kind of like an interactive version of this diagram. So I've made kind of an interactive version of this diagram. So we can move some objects around in the scene, and we can look at their projections onto this projection plane and just explore it a bit and just become convinced, or see how the perspective projection is working, and so on. Okay. So I've prepared some commands in here which we can step through, and I'll also make this sheet available afterwards. So I'll stick it stick the link to it, to this sheet itself, in the comment under the video. And if you want to go and experiment around with it yourself, you just follow the link, and then the link will prompt you to set up your own free account on this system, and then this file will be available to you to edit. And that. When you just click on the link first, it'll just give you a read-only version of this. You can't interact with it or change the commands, but once you set up your own account on the system, which is completely free, and there's no paid version of it or anything, it's just completely free and accessible, then you'll be able to get in and experiment with it and do your own programming with it as well. Now, it's not MATLAB, it's Sage, so it's a slightly different programming language, but I mean the principles are still the same. Now we're not going to do any alignment here. We're just going to set up the world as if it's already aligned. So we're going to have the viewpoint at the origin. We're going to be looking along the z-axis, and we're just going to place some objects in the positive z half of the three-dimensional space, and look at their projections. Okay. Now I need to explain to you how it is we actually go about representing these objects, and this is how more or less how I want you to do them in the assignment. So for this example here, we're just going to deal with some simple cubes. So the first cube I want to draw So this is the kind of setup. I've got the X and Y axes here and the Z axis going into the screen. So the screen is the computer screen we're going to be talking about here is this XY plane, and the Z axis is going into the screen. And so this is the viewpoint here, and it's looking along the Z axis. Okay. So we're just going to deal with a very basic type of object, cube. And the first cube we're going to deal with is going to be centered on the z-axis, but just at a bit of a distance away. How far away have I made it? I've made it 5 and 7. Okay. So some coordinates that I'm going to start plotting out here. Well, first of all, we're just going to label the vertices. So these, the 4 vertices on the front face of the cube and the face of the cube nearest the viewpoint, I'll just label 0, 1, 2, 3. And then the ones behind it, which are further back along the z-axis, I'm just going to label 4, 5, 6, 7. And so the coordinates of these points well, the point 0 here, the vertex 0, that's below the z-axis. So that's going to have a z coordinate of, sorry, it's going to have a y coordinate of -1. It's to the right of the z-axis, so it's going to have an x-coordinate of 1, and I'm going to make it be at the distance z equals 5. And so all these 4 vertices here, will have z-coordinate 5. Okay, because they're all at the same distance from, they're all at the same z distance along the z-axis. So vertex 1 will have the same x-coordinate and it'll be, I'll place it at y coordinate 1. And so 2 will have a negative x coordinate, still be at height y equals 1. And then vertex 3 will be at the negative x and the negative height 1 coordinate. Okay. So they're the four vertices of the front face of the cube. Then the 4 back vertices, 4, 5, 6, 7, they're going to have the same x and y coordinates. Okay, so they're at the same x and y positions, and I'm just going to, now what length have I made the cube? See, I've made the length of this, the side length of the cube 2. So if these front vertices are at z equals 5, the ones behind them should be at z equals 7. Okay, so this is the cube of side length 2. Now, that just defines the vertices. The vertices of the cube is one thing, but then we also want to define the sides of the cube. Now, this is slightly different to how you're going to actually do it in your MATLAB code, kind of, but it's the same idea. So then we'll also specify the lines that make up the cube, or the edges, the lines or edges. So you can see there's how many edges? There's 4 and 4 and 4. There's 8 edges that make up the cube. And we just simply specify them just with the vertex labels. So there's an edge, so the edges then are 0, 1. So these aren't coordinates, these are vertex labels, vertex label pairs. That's how we specify the edges, vertex label pairs. So there's an edge 0, 1, there's an edge 1, 2, there's an edge 2, 3, and then there's the edge back from 3 to 0. Then you've got the 4 edges around the back face, the far face, so that's 4, 5, 5, 6, 6, 7, and 7, 4. And then you've got the 4 edges which are parallel to the z-axis, aren't you? Which are going, so these ones here. So that edge there is 0, 4. This edge up here is 1, 5. And you've got 2, 6. And lastly, 3, 7. So that's the kind of combinatorial information for the cube. It's the 3-dimensional locations of the vertices and the pairs of vertex labels which specify the edges. As we'll explain in the second hour, for your assignment, we're going to represent the faces slightly differently. It's because we're going to be using a basic polygon drawing command in MATLAB, we're going to represent the faces as sequence of vertices. So this side face over here will represent as the sequence 0, 4, 5, 1, the sequence of vertices around the boundary of the face. And then there's a command in MATLAB, which I'll show you, which basically just says fill 0, 4, 5, 1, and it'll draw a polygon. It'll draw a polygon and draw the edges of it, which is bounded by that sequence of vertices 0, 4, 5, 1. Okay, so this is how we get the cube into the computer, so to speak. We specify the locations of its 8 vertices, and we specify the edges as pairs of vertex labels. And then in the computer, then we'll use two types of graphics commands. One to plot vertices. Oh no, did we even do that? No, actually, we won't bother plotting the vertices as such. We'll just plot the edges. So we'll just use a basic line plotting command, and it'll just say line from 0 to 1, line from 1 to 2, and that will just draw lines between those positions. Okay. So remember, what we're going to do is try and build up an interactive version of this picture. That command var xyz sets up 3 symbolic variables x, y, and z, which I think I might need to refer to. That's like the MATLAB command sim or sims for setting up symbolic variables that you're going to use in subsequent commands. I'm going to set f equals 2. So f equals 2, f is the distance of the projection plane from the origin. So set f equals 2, and then I set up this graphics object called P. So P starts off as a 3D implicit plot of the subset of three-dimensional space represented by the equation z equals f. So when the z coordinate is equal to f, that's defining the projection plane that's located at z equals f. Okay? X I'm going to allow to vary between -3 and 3, and y from -3 and 3. Well, and z from -3 to 3 as well. And so when I say P, simply it's going to show me what P is. So P is now this three-dimensional graphics object, which just consists of that blue plane at the moment. Yes, where's the origin? So the origin is down here on the no, where is the origin? The origin is right in the middle of this kind of bounding box. It's just drawn that black bounding box just around the plot. So the origin is hovering here in the middle somewhere. See at y equals 0, x equals 0, z equals 0. This is the positive direction along the z-axis, and so we're just looking at the projection plane there. Okay, but it's just empty for the moment because there's nothing in the scene to look at. As you can see, this is why this is like an interactive version of that diagram, and the notes will be able to move it around and see the effect of various things. Okay, then I'm going to define, so this is exactly what we just wrote down on the sheet. Cube is just this list of lists, or a matrix, or an array, whatever you want to call it. So it's a list of these 3 tuples. And each 3 tuples is just the x, y, and z coordinates of a vertex of the cube. Okay, that's exactly what we wrote down. Those 8 vertices from 0 through to 7. These are their coordinates. Now, in programming, you'll probably have written in your MATLAB programs a number of times x equals x plus 2 or something, and you want to increment the value of x by 2, or I equals I plus 1, and you want to add 1 to this counter called I. Well, there's a shorthand for doing that, which is just to say plus equals. So you can say x plus equals 1, and that takes whatever value x had and adds 1 to it and increases x to that new value. So what I'm doing with these commands is I'm adding things to P. Now, what was capital P? P was the three-dimensional graphics thing, okay? At the moment, it just contains the plot of the z equals 2 plane. But we're going to add to it a bunch of lines. So I'm using this line drawing command. And each line, you see, goes between, so the basic format of the line drawing command is draw a line from this first point to this second point. So there's 2 basic arguments to the line command, and they're each elements of this array cube. Now in Sage, in difference to MATLAB, in Sage, the indexing of arrays begins at 0. MATLAB is kind of unusual in that it starts indexing at position 1. Most computer languages start indexing at position 0, kind of a more conventional way to do it. So this first command says line cube 0, cube 1. So that says draw me a line between this point with coordinates -1 or 1, -1, 5, and this point with coordinates 1, 1, 5. That's the first of those edges of the cube that we all for all 12 edges of the cube. 12 edges of the cube. Yeah, all 12 edges of the cube. So that's the first one of those, and we just say color the line black, and so we just got 12 of those commands to give me the 12 edges of the cube. So when I execute all those, it adds all those lines onto the graphics object we're looking at. And I also add onto it the viewpoint, just so we can see the location of the viewpoint in the scene. Okay. So executing all those changes P. So when I say just P now, it's going to show me the new value of P, which is itself, which is this three-dimensional plot. Okay. So you can see there now it's starting to look like that diagram in the notes. We've got the origin here, which is this blue point here. This is the projection plane located at z equals 2, and we've got our first object in the virtual world. And the whole thing is aligned because I'm looking the origin, or we can align it by spinning the thing around. And so we're looking, we can even zoom forward into the diagram. And if I keep zooming in, see that, oh, there's the origin just disappeared. So at this point here, our eye looking at the screen is positioned at the origin, because I'm just zooming in and in. I'm just gone past the origin there, it disappeared. So at this point there, the thing is exactly aligned. We're at the origin, we're looking along the z-axis, and we can see the cube. Well, actually what we're looking at there is already a perspective projection of that real 3D cube, because it is, look, it's living on the plane of the screen. So we're already looking at a perspective projection, but just kind of ignore that for the fact. For the moment, just pretend you're actually looking at the three-dimensional scene. That what you're actually looking extends behind the screen there. So Sage is obviously doing the perspective projection to allow you to see this three-dimensional setup that we've built here. But for the moment, just suspend your disbelief and pretend you're actually looking at a three-dimensional object there. But within that three-dimensional object is the two-dimensional projection plane in blue. That is a two-dimensional object. And we're going to produce on that plane, we're going to produce now the perspective projection of the cube. So that's what I do now. Now, here there's a little bit of programming. Our cube, the cube array above, remember, was just the list of coordinates. First coordinate, second coordinate, third coordinate, and so on. Sorry, the list of vertices. The list of vertices of the cube. First coordinate, first vertex, second vertex, third vertex, and so on. I'm going to build up another set of vertices now, but these are all going to live on the projection plane. These are going to be the projections under perspective projection of each of those vertices of the real three-dimensional cube there. So I just set up an empty list or an empty array initially called proj cube. That'll be the projected version of the cube. And then what I do is I start filling that with the actual values. So this is what for loops look like in Sage. It's actually what for loops look like in the language Python, because the Python is the language that Sage uses. So this is a for loop. Now it looks slightly different to the ones in MATLAB. In MATLAB, you normally say for, and you normally use some integer counter. For I equals some starting value to an ending value. For I equals 1 to 10, you go through the loop 10 times. This is slightly different. This is kind of more kind of abstract in a way. This is saying for every vertex in the cube. So cube, remember, is that list of vertex coordinates that's stored up above. And this is saying for every object within cube. And I'm here now, when I issue this command, I'm calling these objects vertex. So it'll keep repeating these two statements here, these two indented statements. It'll keep repeating these for every example of an object in the list cube. So that'll be every vertex. And by vertex, we mean the list of three coordinates, the x coordinate, the y coordinate, and the z coordinate. If you look at the top level, if you look at one of the things in cube, the first thing in cube is this list here of these three elements, 1, -1, 5. So that's the first example of what's stored in the variable vertex within the for loop down here. Now this is where it actually carries out the perspective projection. Remember, I stored above the I store it above the value 2 into the variable f. F is the position of the projection plane. So here what I'm doing is f times vertex 0. Now, vertex 0 means the first thing in vertex. The first thing in vertex is the x-coordinate of this vertex. So this is f times x divided by vertex 2. And vertex 2 is the third thing in that coordinate. Okay? So this indexing starts at 0. So this is saying make the x-coordinate of a projected vertex be f times x divided by z. And make the y-coordinate be f times, that's vertex 1, that's the second element of vertex, so that's the y. That's f times y divided by z. And then make the z-coordinate always make it f. So that puts this point. So this proj vertex is now a point with z-coordinate f. So it's going to be a point living on that blue projection plane in the diagram that we saw a moment ago. And its x and y coordinates are defined using the x, y, and z coordinates of the original vertex. And they're defined with the correct formula to give the perspective projection. So this takes each vertex from the original cube. It creates a new vertex called proj vertex, projected vertex, which has the correct coordinates to be the perspective projection of that vertex. And then this last command, it says take proj cube. Now, proj cube begins as this empty list. And it says append this proj vertex to it. So append means to take a new element and stick it onto the end of a list. If you append a new element to a list, you take the current list and you just stick a new element in at the end. So this for loop runs through all the vertices in our original cube. It creates a new vertex which has the correct, which is the perspective projection of that original vertex, and it adds it on to this list, proj cube. So when we execute that, that'll zip through all those. So when I say proj cube now, it should show me what's stored in proj cube. So proj cube was empty up here, then it did the for loop, and it populated with all these. So this is now the list of vertices, which should be the projected version of the cube. And notice they all have z-coordinate 2. So these are certainly all points that are living on the projection plane. Okay, at the moment there are just a bunch of vertices. What we now want to do is draw them into our 3D plot P. Draw them into our interactive version of that diagram for the notes. So just as before, I have a bunch of line drawing commands. And I'm adding, so each of these line drawing commands creates a line in the environment and it adds it into the 3D picture P. So do P plus equals each of these lines. So I just copy and pasted the set of line drawing commands I had from the start. When I used them before, they were just cube 0 to cube 1. So I just added this proj underscore to make it use these coordinates. So this draws all, how many edges? 12 edges of the cube. It's still using the same relationship in terms of the vertex labels, but it's now using different vertices. It's using the projected versions of the original vertices. So I execute all those, and now we can look at the 3D environment P, and I drew them all in green. So those things that I've just drawn are all there in green. We zoom in a little bit. You can see now the relationship between the real cube, which is this cube, the black cube, which is the real 3D cube, and there is its perspective projection onto the projection plane. Okay, so that green thing, well, it looks like a cube sometimes when you look at it, but it's not. It's just a collection of flat line. It's just a collection of lines all within the projection plane there. And of course, forget for the moment that you're actually looking at a perspective projection of a perspective projection. Pretend that what you're seeing spinning around there is actual 3D thing wobbling around behind the screen. And you can actually see that it all kind of lines up perfectly. If we align the environment, so now we're looking along the z-axis. The z-axis is, I've spun the box, I've spun the large box, so the z-axis is running away from you. And if we zoom in now, remember that blue point is the origin. So if we zoom in so that we're exactly at the, okay, there it goes. That's the origin just in front of our noses, and then we've moved past it. So we're exactly at the origin now. you can see there that the green projection has lined up exactly with the actual real 3D cube in the scene. So that's what you're seeing now is exactly my metaphor before of when I said you had the sheet of glass in front of you, and you got a marker, and you kind of fixed your head in place, maybe closed one eye, because yeah, this thing is just a one-eyed person. You closed one eye and you drew around everything you saw with a black pen on the sheet of glass, so that the lines you draw on the glass exactly line up with the real lines you're seeing in the environment. And so you can see exactly that there. Our eyes are now exactly at the origin of this thing. Okay, so the box, you've zoomed into the box. The box is just right at your noses. And the green perspective projection on the projection plane exactly lines up with the scene. So that's nice. When you go in and experiment with this, you'll be able to spin it around and stuff and get a nice idea of it. I've just enhanced it a little bit. I've created a second cube here, which I've called transcube, which is just to stand for a cube which has been slightly translated. And I've translated it by adding, as you can see, so this is like the perspective projection loop, except this time I'm changing each vertex by adding 3 to the x coordinate. So that just should create a new cube now, which is just shifted to the left or right by 3 steps. That creates a new set of vertices. And the x coordinate has been shifted by 3 in the x direction. Have a new bunch of line drawing commands to draw all the lines between the vertices of that translated cube. And then I can look at our 3D plot again. So there's the second cube, shifted 3 spaces to the right of our original real 3D cube. And then I can get the perspective projection of that. I just copy and pasted the commands from before, except this time dealing with for every vertex in the trans cube, in our translated cube. So I build up this list of projected translated cube vertices. This is the same f times x over z, f times y over z, f. That's the perspective projection there. So that generates a new set of vertices, which are all on the projection plane. So they've all got third coordinate f, which is 2. And this, now I draw the lines, which will all be lines on the projection plane. I make them red so we can distinguish them. So I've added those there to the graphics object P. And now when we look at it, so we can see the actual environment there. You can see the projection plane, and you can see, zoom in a bit, you can see the projection of the second cube. And of course, from the viewpoint of the origin, the second cube isn't straight on at the origin. It's slightly off to the side. So you're seeing it looks different. The red 2D projection is kind of askew because the cube is off to the left or whatever. Okay, and it still lines up perfectly. When you zoom in, you have to spin it around. It's kind of awkward, but when you zoom in and you hit the origin exactly, where's it gone? Just the mouse isn't quite accurate enough. Okay, that's more or less it. Okay, the mouse is a bit clunky, but just at this point here, we're exactly at the origin. Our eye is exactly positioned at coordinate 0, 0, 0. And you see both projections, give or take a little bit because of the skewy mouse, both projections exactly line up with the real 3D images in the scene. Okay. So if you needed any convincing that what we were doing was actually perspective projection, hopefully this has cleared it up a bit and given you a way to help to think about it. So I'll make this whole sheet available now. This will be available as a link in the comment to the lecture recordings, so you'll be able to go in and experiment with this yourselves as well. Okay.